So let's get started. Make sure I'm on the right one. I am. Well, good afternoon, everyone. We are going to start today by doing the syllabus. Now, our class is basically broken into two chunks. Canvas is where I put all the resources, things that will help you. That's where the videos are stored. That's where you'll find links to Zoom and help pages to, troubleshoot WebAssign or whatever. And that's what you're looking at right now. And then the other half is WebAssign, which is over here. And there's going to be a little bit of overlap because we're going to be starting at partial derivatives, which is where we ended off last time. But there's a little bit more added to the partial derivatives and a little bit more added to the chain rule as well. So it's not exactly the same as the last week, but there is a lot of similarities going on. So let's close that off and back here. So first page I would go to, although most of you know me, so this is really just duplication, but not everyone here got me last quarter. So for them, it is brand new. So for their benefit, I need to do this. What we're looking at here is the welcome one, and it basically tells you everything you need to get started. This is the technology that you need. You do not need a textbook. We're WebAssign, and WebAssign has an ebook, so you don't need a textbook unless you want to get one. And this is the class key for us. I haven't looked yet, but I would hope by the end of today that you're all on WebAssign and that you've checked in. So what goes on in WebAssign? Well, that's where all your homework is going to take place. That's where your class tests are. So if you remember Calc 3, it's pretty much the same. There's a 2-week grace period, so you don't actually need to pay money. I think it's 2 weeks anyway, 14 days. And during that time, you can find out whether this class and this method of teaching suits you. And I like the fact they have that grace period, because if it doesn't work for you, you can drop the class, but you won't have spent money, right? You won't have, joined WebAssign, spent what? Anybody want to share how much is it to get a class in WebAssign? 100 and something? 100 and something. There are different versions of it. Do you know you can get like a yearly subscription, and that way you can do lots of different classes? Probably wouldn't be a good idea for you lot because you're at the tail end of your career, but if you were doing Calc 1, it probably would have been cheaper to do it that way. Anyway, it costs you whatever it's going to cost you, and this is the class. And here are the instructions that you will follow to join, which are pretty much what they were before. Here is officers. In this case, what does that say 11 for? I'm going to have to fix that. It's 9 o'clock. Officers are 9, not 11. There's our link to this fella. And Canvas has lots of resources in it. So let me show you some of the resources. If you click on this link, this is where all the class lessons that we take are going to be stored. So for instance, here is going to be our first one, right? That's going to go there. And that'll probably be online at the end of today, if not by tomorrow morning. And there's the officer Zoom link. And this time I got it right, 9 o'clock. And if you have trouble with Zoom or WebAssign, you really don't need to worry about that until we get to the midterm. And there's a nice fun stuff. Now, if I close this one off and I go class resources, what you have here are essentially the 3 chapters that we cover, 14, 15, and 16. And if you click on these chapters, you get other people's versions of what I'm doing. I don't know why that's staying. So there we go. The reason why there's two versions of this is that one of them is, I think it's the top one is the normal one, but the second one has closed captioning added. So if we have someone who needs that, that would be your choice. And if you click on them, you get various people explaining the same topic in different ways. And there are all sorts of pages here. Let's scare you. There's a formula sheet. Should load up eventually. Oh, it's slow today. And there's a whole load of weird squiggles. But I hope at the end of 10 weeks, those weird squiggles will actually mean something to you. But right now, it's just gobbledygook. And that's not a surprise. Some tons of different types of online software. That one, these are for drawing three-dimensional surfaces. This is things called vector fields that we'll deal with. This here is contour plots. So if you wanted to do, I guess I'll click on that one just to show you what it's like. There we go. That's what a contour plot looks like. And if you're wanting to draw one, that would be the place you'd go. So tons of resources. Close this one off. If you click on this one, you get college resources, which is basically all the things the college does for you, like tutoring and so on and other help. And let's move over to the syllabus. Usual issue, will you just email me at my college, drobertson@olympic.edu, or use Canvas. Don't use WebAssign. Even if it has a button that says ask my professor, don't hit it because I won't see it and I won't be able to answer your question. There's a zinc loom, and again I got it right, so there's only one place I need to fix for the officer. And you shouldn't be able to take this class unless you've got a prerequisite. For most of you, it's you passed 163 and got a 2.0 or better, but for some of you it might be some kind of test like Accuplacer or whatever. Stuff you need. If your computer dies on you, you could get a loaner from the college. You don't need textbook. This is duplication of information. There's the key to get into our class. The key dates: holiday, Friday the 13th, and Monday the 30th is a holiday. And the midterm is Monday the 9th, and the final for our class is Wednesday the 15th. Now, here is our kind of rough guide to what we'll be doing over the next 10 weeks. Everything is broken into week chunks. This week is basically the last week of 163. We're going to do partial derivatives in the chain rule, and there's your test. All of this is on WebAssign, as all homework is. You can spend as much time as you like on the homework, as long as it's done by Sunday midnight. And the online test, it won't appear until Friday or Saturday morning. And whenever you do the online test, the minute you click on it, you get 2 hours to finish it. So make sure that when you do that, you're ready to, do the whole thing in one go. Homework doesn't matter. You can come in and out as often as you like. In the homework, you get, I think, 5 guesses, and it'll tell you if you're wrong. In the online test, you get guesses, but it won't tell you if you're right or wrong. Week 2, week 3, week 4, week 5, there's your midterm. Midterm will be on ground. It will be in class, and it will be, I think it will be a 2 or a 3 hour. I haven't made up my mind yet, but it will start at 12 and finish at 2, or start at 12 and finish at 3. And it's just like you did the final, right? It's Zoom, and it's going to be a PDF, and I see all your working, and you upload it. And the final's an exact carbon copy of that, and that is a 3-hour. And then you do weeks 7, 8, 9, 10. Monday technically is a school day. That is exam week, and that's just going to be turn up if you have any questions for the reviewing for the final. A lot to take in, but this video is being recorded, so you can always go back and look at it. Plus, you can go to Canvas and read things. So don't worry too much if you think you're getting overwhelmed. Right, here are the things that we're going to be doing in Calc 4. Right. If you remember when you took Calc 3, I said, look, Calc 3 is really just a whole load of stuff that aren't connected to each other, all shoved into a class. So you've done sequences and series and you finished with that. And the good news is that Calc 4 has a theme. Calc 4 is all about multivariate functions, how to differentiate and integrate. In other words, how to find partial derivatives and how to integrate things. And the applications of those. So if you are going to be an engineer, this is the calculus along, well, I would say differential equations is even more important, but along with differential equations that you're actually going to be using in your engineering life, right? I've taken this class lots of times, and I've had people telling me in the shipyard workers, for instance, they'll tell me things like, yeah, we need to calculate flux. You haven't a clue what flux is, but you will eventually know what flux is. And they say, yeah, we need to know that. Or we need to know the center of mass of a three-dimensional object, right? A boat is a three-dimensional object, right? It's a good idea if you know where its center of mass is and all sorts of things. So they've told me frequently that this has been really helpful for them because in the past, they were kind of just told this is what the thing was, but they were never given any math of how they found it. It's a bit like they just told you this is what this is the volume of this thing. Trust me, I'm a mathematician. Well, they're now becoming that mathematician that says to the other engineers, trust me, that's its volume. I'm a mathematician, right? Because not everyone needs to know why something is equal to it, although it's useful. And it does a lot of stuff in vectors. It's really 3D. It's the calculus of 3D, which if you think about it, isn't that what the real world is, right? It's three-dimensional. And up to now, hasn't the world been two-dimensional? X, Y. The calculus has been. If you have any need for disability that we need accommodations for, tell me about it and I'll make sure you get it. Let's talk about the grading. A little bit different. Every time I try different things, I tweak it. Participation grade is 10%, and that is a typo. That should say 50. So there are 50 class days. You get 1 participation point for every day. And we take attendance the usual way. You put your last name down in chat. So Mia is going to put Spandler down when we come to that. And instead of extra credit in the usual sense, I've included the extra credit inside participation grade. And the way it works is every week you do not ask for an extension, right? You do your homework in time. You get 1 participation point. So theoretically, you could get 120% in participation. If you miss a day, but you don't do, but you do the homework in time, the participation point is a bit like missing a day, right? It fills the hole up for missing a day. Right? So it kind of works that way. So if you miss 4 days, but you do all your homework on time, you'll still have a +6 on the participation scale. You see how it's going to work. So I think that's for me, I think that's going to be a better way to do participation, right? You've came to class or you've done the homework, right? You've participated in the homework. And homework, 20% of your grade. Online tests, 20%. Your midterm, 20%. And your final exam, 30%. And add them all up and you get your grade and decimal version turning into a letter. We have tutoring. I'll be honest with you, when you get to when you move higher up the food chain, i.e. Calc 4, it's much harder to get tutors. There are very few people who know Calc 4 stuff, right? But we do provide tutoring, and hopefully there's someone who is doing Calc 4 tutoring. There's also e-tutoring, right? So you might be able to get someone, someone who might be doing their bachelor's right now might help you, right? Because that's probably the kind of person you want. You'll know how to do e-tutoring, right? You can just go into the computing web, OC's website and find the tutoring and then click on it. And Maggie told me it's a bit like an officer. You just click in, you wait till it's your turn, and you see someone and you ask them their question. I'm assuming you can do things like share your screen and so on. Right. See me, officer, or just contact me by email. There are a lot of resources on Canvas. You can even have phone a friend. Right. So me and Maggie will be phoning each other frantically about homework from time to time. Oh, did I guess that right? Do you two ever phone? No, okay, maybe you should, right? Whatever. If you want to, there's no need for you to. WebAssign does have videos that you can watch and so on as well. I think anybody who's got to Calc 4 must have figured out these things, like do your homework as soon after a class is finished so that it's fresh in your mind, plus you know if you really do understand it. Make sure that you're ready for all your tests, even the class tests, the online tests. Prepare for them before you do them and give yourself plenty of time. Don't wait till the last minute to do anything. And seek help whenever you can, as soon as you can, and especially towards the midterm and the final, because those are huge points that you try and figure out some way, again, extra time to get ready. And that is it. I think I've covered everything obvious, but I may not. Any questions before we start our lesson proper? Are we good? It's mostly like what I did before, right? And then let's close this off and start our lesson. The good news is you've done a lot of this before. I'll just check that off my list. We're going to look at finding partial derivatives. Right, so we got a multivariate function. They can be written in a number of ways. The two most common ways for doing a three-dimensional surface is to write it down, something like that. That would be an example. Or you sometimes get it written using this notation. And these are essentially three-dimensional functions because, especially when you see it this way, for any given x and y, there is a corresponding z value. And so if you imagine what that might look like, that's the way that we draw or try to draw three-dimensional surfaces, right? Using the x, y, z. These shapes, these relationships don't generate lines or even curves in 3D space. What they generate instead is what we call a surface, right? It's a curved, like flowing hills in England, right? Ups and down bumps. That's the type of thing. And when we find partial derivatives, we're basically taking that surface and splitting it either parallel to the x-axis or parallel to the y-axis. And then at that given cross section, we're finding the slope of the tangent line. So if you're trying to visualize what is the partial derivative of f with respect to x, sometimes called f little sub x, you're slicing the surface parallel to the y-axis actually, and then looking at that particular point, what the slope of the tangent line is. Now, let's see if I can use one of our pieces of software to do that. I'm just setting it up right now. Hopefully that's not too scary, but who knows what we're going to get. And that one looks interesting as well. I might do that. So I'm picking right now. Let's do GeoBra. Okay, all right, and I'll switch over. Hopefully you can see it. Let's look at what one of these surfaces look like before we start doing the derivative. Right. So hopefully I can just do z equals xy squared. Oops, already did the square. Right. So that's xy squared plus yx squared. There, that'll do. Now, this blue surface, if you orientate it, can you see how complicated that shape, that surface is? Right, you see it's got a lot going on. I mean, if you look at it vertically above, it's quite different than you see it side on. But rotate a little bit, you see it's a little bit different again. Can you see that this surface has got a lot going on, right? But that's essentially what you are dealing with in the 3D world, right? The surface part of a shape like this. Let me turn this guy over into something a lot simpler, which is this shape here. Click off it, there. Now, would you agree that's a much nicer surface, right? Now, can you imagine if you sliced that surface parallel to the y-axis, wouldn't you have a big parabola shape? And then if you picked one point in that, wouldn't there be a tangent line? That's the derivative dz by dx. That's what it would be, the value of that. Now let's return to how do you do partial derivatives? Well, the good news is you already know. Don't you basically just take the function, and if you want to find this partial derivative, don't you consider x a variable and everybody else a constant? So in this question here, right, if I wanted to find this partial derivative, you differentiate x squared, you get 2x. If you differentiate xy, right, with respect to x, don't you get plus y? Isn't it like 5x gets you 5? And what would e to the power of y get you? What's the partial derivative with respect to x of e to the power of y?
Nothing.
Yeah, and we don't write nothing, right? So that's the answer. Now, if you did a partial derivative of that same function, but now you did it with respect to y, wouldn't the x squared get you nothing? Wouldn't this guy? Well, what would this guy get you if you differentiated it with respect to y?
X.
X, right? And wouldn't e to the y just get you e to the y? Not doing anything too strenuous right now. So we know how to find partial derivatives. You basically just use the same rules of differentiation, right? Product rule, quotient rule, chain rule, right? All those rules. All you have to remember is that there's only one variable at a time, in this case x, and you treat the other guys or guy as a constant. Now, if I did this one here, and I asked you to do the partial derivative with respect to x, this term here would get me y squared. This term here would get me 2yx, and this term here would get me 0, right? With respect to x, sine of y gets me 0. I guess I should do the y for completeness. If you differentiate this with respect to y, you get 2xy. If you differentiate this with respect to y, you get x squared. And if you differentiate this with respect to y, you actually do get something. You get cosine of y. Now, as long as you are familiar with and comfortable with product rule, quotient rule, power rule, chain rule, right? The usual Calc 1 differentiation rules. Isn't partial derivatives just another extension of that idea, right? You're still differentiating, but one thing is a variable and every other letter of the alphabet that you might see is a constant. Kind of what we did last time, right? We're going to do tons more practice of those over the next few days. And one of the reasons we're kind of beating a dead donkey, or whatever you want that phrase is, I can't quite remember. You really want to be good at this because you're going to be doing this a lot all the way through, right? At various places, you're going to be finding partial derivatives. So we want you to be really comfortable. Yeah, not a biggie. I can do that without thinking, right? So let's up the ante and start making functions that are more difficult to do partial derivatives of. Right, here's a pretty messy looking function. And I would like to find the partial derivative with respect to x. So each one of these terms we're going to treat separately. I think that's the best way to tackle it, right? And find its derivative where x is the variable and everyone else is considered a number, a constant. So if you do this one, wouldn't x squared get you 2x, but that sine y is still there, great. Shift along. Now this one here, with respect to x, right? If you differentiate this expression with respect to x, any volunteers? Be careful. It's about like 5e to the 5x. That's equivalent. That's what that's like. ye to the xy. Any volunteers?
Would it be y squared e to the xy?
It would indeed. And put you through, I'll write it up here in red, the kind of middle stage that would go in your head, right? ye to the xy. You'd get ye to the xy times the derivative of xy with respect to x gets you y, and those two guys get you the y squared. You all happy with why that is what it is? Right. Now, if you do x plus 2y cubed, aren't you essentially doing a chain rule? Right? Now, in this case, that's 3 lots of x plus 2y squared. Technically, shouldn't you then multiply by the derivative of what's sometimes called the inside function? Well, in this case, isn't x plus 2y just 1? So it really isn't there. So I really should tidy it up. Not that I can actually tidy up that much. But if you did it in your head, wouldn't you not need that middle line? You could do it straight into the end line. We're going to do the partial derivative, but this time with respect to y. Would you agree that you found out when you did it last time that the two partial derivatives, that's this one and this one, aren't they very rarely ever equal to each other? In fact, you could almost guarantee they're never going to be equal to each other. Great. And so don't expect too much of the same thing happening. Right? So back to each term, but this time with respect to y. Right, x squared sine y becomes x squared cosine y. Now, this term here is messy. It's so messy that I'm going to do it on its own, like a bit of scratch paper. If you want to differentiate this guy with respect to y, would you agree it's a product rule? There's two things. There's a y
That's
squared.
supposed to be just regular y, right? Not y squared.
Oh, thank you. I scanned the wrong place. Now, would you agree that this is a product rule? It's got a y here, so I'm calling that f, and it's got an e to the xy, I'm going to call that j. So product rule is still the product rule, right? The formula doesn't change. If you differentiate this guy with respect to y, you get 1. You leave this guy alone. You leave this guy alone. And now you have to differentiate e to the xy with respect to y. Now, if you differentiate e to the xy, you get e to the xy times the derivative of xy with respect to y. And doesn't that get you an x? Are you happy where that x came from? The derivative of xy with respect to y is x. And so that would tidy up as this guy plus that term. And so this middle term ends up being e to the xy plus xy e to the xy. Now the last term, again, it's going to be the chain rule. Now if you look at this fella here, it's 3 times x plus 2y squared times the derivative of the inside function. Now the last time it was 1, but I'm differentiating the inside function with respect to y this time. So what will I get when I do that? I won't get 1. What will I get this time? Well, I've seen the lips move. And they said 2. Yeah. Now, tidying it up. That guy's already good. That guy is good. That guy is good.
Mr. Robertson,
Yes.
won't you also have a 2 from doing the product rule, or from bringing down the exponent? So wouldn't it be 12?
Oh, dang. Well, 3 coming down makes that a 3, so I'm good. Make that thing go away.
Oh, gotcha. Sorry.
Yeah, yeah, I'm bad at scanning as well. Having a previous answer to structure, right? That's good. Style points, which is something, you know, I push a lot, is not going to be a big deal in most of these questions. Would you agree that most of the answers are so ugly, there's nothing you can really do to make them better? But you should be in the lookout for the odd, you know, combine 2 terms together. Maybe once in a blue moon, you might be able to pull out a common factor, but don't expect it to happen too often. So most of the time, the ugly answer you get is as good as the answer is going to be. So style points won't be such a big deal because of that. Are we good so far? What I'm going to try now is I'm just going to jump and pick a function to find its partial derivative. So still on first partial derivatives. I don't want to move away from that anytime soon. I'll randomly pick a number. Ooh, that's a good number. I like it. And this is a version of question 7. Wow. You've been asked to find all 3 partial derivatives, but I'm just going to pick one of them. Let's find the partial derivative with respect to z. So I have got y tangent of this. And since I'm only interested in the partial derivative with respect to z, isn't y and x just numbers right now? So if you want to differentiate y tan of something, you get y times, and this is where memory kicks in, right? You just have to remember, what is the derivative of any tangent? Come on, don't scare me. Derivative of a tangent.
Is it secant squared?
Well done. Did you look that up or it just came to you?
Nah, I figured I'd take a leap and hope I was right.
Okay, it was a good leap, a leap of faith, and you got it right. Do you know there's a big table somewhere that you could probably print out somewhere until the best thing is just to memorize the damn thing. So it just speeds your life up. Because you know, when you've got complicated things to do, if you keep having to interrupt the thought process by going to have to find the derivative of a tangent, isn't it much harder to keep the flow going in your brain? You know, so just try and focus on memorizing as many of them, at least the common ones, as you can. Now, this isn't finished because this is the tangent of something. So technically speaking, shouldn't we now differentiate by the inside function? Now, with respect to z, this actually ends up being something, doesn't it end up being 4? And that times 4, I guarantee I'm going to miss that times 4 a lot between now and the end of the quarter, but this time I got it. And so the partial derivative with respect to z then is 4y secant squared x plus 4z. And that is a pretty common rule in style points. You always write style points from simplest thing to ugliest thing. So numbers, you know, x's and y's, x's and y cubes, and then the ugly stuff, right? The secant squareds and the square root stuff at the end. And that's the typical order that you should write things as style points. And that's still there, right? You're going to have to do that a lot of times, right? Just to rearrange the answer so it looks, you know, that's not really that, right? You know, that's the right answer. That's an ugly version of it. How about this function? Pick some, everyone's a little bit different. This function is in fact technically a 5-dimensional function because 4 variables plus the function itself considered a variable. In this case, it's x to the 4 with a y times the cosine of z over t. And I'm going to do 2 of these guys. And I'm going to use this notation. And that's the first one. And I picked that one because it's the easy one. And then the next one I'm going to pick is the ugliest one, right? So this is the easy one. Would you agree that everything that my fingers are covering is really just a constant? So isn't this like 5x to the 4, right? It's just a power rule. So multiply by the power and reduce the power by 1. Right? One-liner, didn't need to think about it, pretty straightforward. Anybody good at predicting what variable I'm going to pick for the ugly one? Because I know what one I'm picking, but what one do you think I'm picking?
Is it
T?
T?
It's a t. Why am I picking the t? Because isn't it in the ugliest place possible for differentiation, right? So watch me because I make mistakes. This bit is the easy bit. Isn't that basically like 5 cosines, right? So if you differentiate a cosine, you get a negative sign. So it's going to be a chain rule. So far, so good, right? Negative xy cosines gets you negative xy sines. But then don't you have to finish with the derivative of z over t with respect to t? Now, if something is ugly or weird or just doesn't make a lot of clear sense, take a piece of scratch paper and take it on its side and say, okay, that's the guy that I want to differentiate. If I want to differentiate that guy, wouldn't it be a good idea to rewrite it as a negative 1 power? And if you write it like that, can't I just do the power rule? And the power rule is multiply by the power and then reduce the power by 1 and then make it look pretty. Are you comfortable about the derivative of that is this guy? Okay, that z over t, it's with respect to t, is negative z over t squared. And so that goes here as a negative z over t squared. And then I just tidy it up. 2 negatives make a plus. I put the z there, the x to the 4, the y. I guess I could mix and match them. the sine of z over t, and the whole thing, it's a big ugly fraction, right, is over t squared. Are we good with that? Is this second guy mathematically equivalent to this one? Agreed? Visually, does either of them look prettier in your brain? Would you say the second one looks a little bit prettier? Right. Weber's sine has got lots of little idiosyncrasies. The reason why I'm kind of showing you these two versions is I can imagine in some questions, Weber sine likes this, but tells you you're wrong when you write that. Or it likes this, but it tells you you're wrong when you write that. You're not wrong if you write this or that. Would you agree you're right in both cases? But Weber sine has idiosyncrasies, that's the best phrase I can think of right now, where just because it tells you you're wrong, will you have a double check and think maybe it's just the way I've written it isn't the way I wanted it to be written? And try that as your alternate guess rather than, well, in this case, it wasn't too bad, but can you imagine a question you spent 15 minutes getting the answer to, right? And the answer ends up being this, but they wanted that. Can you imagine you don't want to do the question again, right? Another 15 minutes just to find out that you can't change anything. So think about alternate versions of the same answer. I think if you do, I keep forgetting that term. Do you know, give me another example? You know, those guys. Look at how they wrote the answer, not the answer itself so much, but how they finished it. And if it looked like that, type your version. And if it looked like that, type this version, right? That might be a way of getting around the idiosyncrasies that Weber sine has. Now, it doesn't do it a lot. I know there are a lot of situations where won't it take both and everybody's happy. But just, you know, I don't want you to get frustrated on, I'm doing this right, but it ain't accepting my answer kind of thing, right? If it was a person, couldn't you just shout at them? But since it's a piece of software, it doesn't know that you're frustrated. So you won't be able to help it. Are we good with that one? Right. Yeah, I'm just randomly picking things with things wrong with it, whatever the word is. Let's pick another first derivative of weird thing. Yeah, last one for today. Version of question 3. So why did I pick this one? Well, I'm going to do a partial derivative with respect to y. Would you agree this is a product rule? Would you also agree that there's going to be some chain rule stuff happening? Right. So that guy I'm going to call F. This entire ugly thing is going to be called J. So we're going to do the product rule, which we're comfortable with. If you differentiate this, you get 1. Leave this guy alone. Leave this guy alone, you get y. Now, this is the guy that I'm talking about is a chain rule. Would you agree this is a chain rule question? So you multiply by the power and you reduce the power by 1. And then don't you finish with the derivative of the inside function with respect to y. So what do you get if you differentiate x plus x squared y with respect to y?
X squared.
You get x squared. Now on this line, I'm taking this really slowly. You probably wouldn't read anywhere near as many lines as I'm doing. And the reason why I'm doing that is that this does have some style points. Right. Would you agree that I can pull out a common factor? Right. The general rules are still true even in partial derivatives. Make me look like the original. Factor the heck out of me. And if it's a trig identity, try and find, some way of making it simpler. Right. This fella has an x plus x squared y to a 4 and then to a 3. Would you agree that this is a common factor? But what power can I pull out? What power of this expression is a common factor?
To the third power.
Right, always the smaller, correct. Which leaves me with that guy plus that guy. Are we good? And you might, and unfortunately WebAssign will do this, it might say you're correct, but I think I can do better. Remember, it's factor the heck out of me. Can you see anything else that can be factored?
X.
Right? I can pull out an X. I'm going to put it there so I don't have to rewrite a line. And if I do that, I'm going to have a 1 plus an XY plus a 4 XY. And sometimes you don't notice it until later. Do you notice anything? Do you notice anything?
The 4xy and the xy can combine to get 5xy.
Yeah. So it's now going to be 5 and 1 plus 5xy, x plus x squared y cubed. Do you see there was a lot of style points in that? A lot more than I was expecting when I picked it. I picked it because I knew there was going to be a product rule and some style points, but I didn't realize how much there was. Now, I'm 99% sure that WebAssign will not like this answer. Would you agree even WebAssign would realize that that and that should be 5? Right? I'm pretty sure of that. I don't know if WebAssign would have taken one of these earlier versions. Even if they did, fight your way to the end, because that's what I'm looking for in the tests, right? The midterm and the final. Okay, well, most of you know how to do this, but for those who are new, in chat, put just your last name down. And David, for instance, he'll put Woodland down. And that is us for today. And I'll see you tomorrow, where we'll continue with partial derivatives. And are we not learning some cool stuff? And I only made one mistake today that I know of that counts as math. So I'm kind of pleased with myself. But the term is young. Bye-bye.